The next topic in this section is on monitoring the rate of reaction by pressure. In our last class, we talked quite a bit about monitoring the rate of reaction by color. We looked at an example of a reaction that had one colored reactant, and all of the other reactants and all of the products were colorless. So you could use the gradual fading or diminishing of the color of the one reactant molecule to get information about the rate of the reaction overall. And in lab on Monday, you're going to do an experiment that has one colored product, and you're going to monitor the appearance of color and use that to get information about the rate of the reaction. You can do a similar type of experiment with monitoring the reaction's pressure if you have, obviously you have to have a gas phase component in the reaction, otherwise there isn't any pressure to be monitored, and it's going to work best if you have only one gas phase component in your reaction. That way you know that all of the pressure that's being created or all of the pressure that's being decreased is due simply to the production of that one gas phase component or the consumption of the gas phase component, whether it's a product or reactant. For example, the decomposition of hydrogen peroxide, which has aqueous hydrogen peroxide turning into liquid water and oxygen gas. Because this reaction has only one gas phase component, you could easily monitor the rate of this reaction by looking at the pressure. As this reaction proceeds, the oxygen gas is going to be produced, and it's going to cause the pressure, if it's in a closed container, the pressure to increase. And you can relate that increase in pressure to the concentration of the oxygen gas and use it to calculate the average rate of the reaction. All of the average rate of the reactions equations that we've looked at so far have all had this general format that goes rate equals the change in concentration of the product over the change in time. And for gases, we typically don't talk about gases in terms of molarities. We usually describe gases in terms of pressure, but we can use the ideal gas law to derive a relationship between pressure and concentration. So if you look at the ideal gas law, PV equals nRT, and you do some pretty basic algebra to it, just rearranging the variables, you can see that N over V equals P over RT. N over V is moles per volume, and in the ideal gas law, V, the volume unit, is liter, so N over V is moles per liter, and that also is the units of molarity. So we can substitute N over V for the concentration of O2, and we can then say that the concentration of O2 is equal to the pressure over R times T. The pressure of a gas is very easy to measure, and obviously the temperature of anything is very easy to measure, so it's quite easy for us to calculate the concentration of O2. Once we have redefined the concentration of O2 in these terms, we can then plug them into our generic equation for the average rate. Again, as a refresher, the average rate of this reaction is going to be the change in concentration of the product O2 per the change in concentration of time. And again, this is a positive value because O2 is a product, it's being produced, its concentration is increasing, so this is going to be a positive number. And we're just going to plug in our value of our redefined term for the concentration of O2, P over RT. So we're going to say that the rate of the rate is equal to the change in concentration of O2 over time, which is equal to the change in the pressure of O2 over R times the temperature T, all over the change in time. Now the gas constant R is a constant. It's not going to change over the course of this reaction. So we can just pull that variable out of this term, the changing term, and we can say that the equation is then 1 over R, the gas constant, times the change in the pressure over temperature, all over the change in time. Now, if we're smart and we hold the temperature constant, which is very easy for us to do, we can pull that temperature term out as well, so that we have 1 over RT, here the T, capital T is temperature, times the change in pressure over the change in time. And again, this is only going to work when temperature is being held constant, but it's totally worth it to hold the temperature constant so that you only have 2 changing variables that you need to monitor. And that's all that we're going to say about monitoring a reaction by pressure. The next topic, and the last topic in this section, is the relationship between reaction rates and stoichiometry. All of the equations that we've looked at so far, well, that's not necessarily true. The generic equations that we've used to help us define these kinetics equations and concepts have all had one-to-one stoichiometry. So for example, we looked at an equation that was A goes to B, 1 molecule of A going to 1 molecule of B with one-to-one stoichiometry. And we looked at A plus B goes to C, which also has one-to-one stoichiometry. When you have stoichiometric coefficients other than 1, those coefficients affect the rate of the reaction. For example, this generic reaction, 2A goes to B. Because of the stoichiometry of this reaction, reactant A is consumed twice as fast as the product B is being made. And this makes sense. It takes 2 molecules of A to make 1 molecule of B, so you're going to run through the A molecules twice as fast as you produce the B molecules. And this difference, or this the stoichiometry of this reaction, does have an effect on the numerical value of the rate of the reaction. So if we just take the rate of the reaction with a very simple definition, change in concentration of A over time, change in concentration of B over time, we're going to see a difference in the numerical value of rate when we're looking at it in terms of A, as opposed to if we're looking at it in terms of B. Reactant A is going to be consumed twice as fast. Its rate is going to be twice as fast as the rate of B. And that's not useful to us as chemists. We want to be able to define the rate in terms of the whole entire reaction. And we want the rate to be the same whether we're looking at A or whether we're looking at B. So when we have stoichiometry, that affects the rate at which a reactant is consumed or a product is produced. We have to correct for the stoichiometry, and we have to correct for this difference in the rate of change. If we look back at our generic equations for the average rate of change for this particular reaction, you learned that the average rate is equal to the negative change in concentration of reactant, A in this case, per change in time, and that the rate is equal to the change in concentration of product B per time, positive, because this stuff is being produced. These two numerical values of rate are not equal to each other because A is being consumed twice as fast as B is being produced. In order to make the numerical value of rate equal to each other, we add a 1/2 to this side of the equation, and we just say, as fast as A is being consumed, take that number, cut it in half, that's the rate that B is being produced, and we're going to call that number rate. So essentially, we define the rate of reaction in terms of the change in reactants or products that have a stoichiometric coefficient of 1, and everything else that has different stoichiometry is corrected for. In general, for a generic reaction, little a plus little b goes to little d plus little e, where the little letters are stoichiometric coefficients and the big letters are the molecules. The rate of reaction can be defined as the negative 1 over A times change in concentration of A over time, 1 over the stoichiometric coefficient times the change in concentration per change in time. Or for the products, the same thing, only it's a positive number, 1 over the stoichiometric coefficient times the change in concentration over the change in time. And this allows us to correct for any stoichiometry that might be present in the overall reaction. This is the end of section 13.1, and next we're going to do section 13.2.